In Chapter 16, we looked at covalent bonding. How do you take nonmetals and bond them together? It's not an ionic bond where you have a metal from group 1A or 2A bonding to a gas in group 6A or 7A and forming a salt, like we talked about in the last chapter. Covalent bonding is a little different. Instead of transferring an electron from one atom to another, the two atoms share an electron. Okay, they might share it unequally. One might be a little more electronegative than the other and pull the electron closer to its nucleus than the other atom, but it's still a sharing. Okay, so what we're looking at with covalent bonding is how do nonmetals share electrons when they bond? All right, let me give you an example of what I'm talking about. Let's just look at some of the diatomic molecules, like hydrogen. Hydrogen in nature exists as H2, two hydrogens bonded together, because they're more stable that way. Okay, one hydrogen, if I draw the Lewis dot structure for it, it would look like this. Okay, it's the symbol H for hydrogen, a valence of 1, because it has one electron, and that would be its valent electron, okay, buzzing around the nucleus. That's not as stable as if two hydrogen atoms come together and share that pair of electrons. That's an example of a covalent bond. So these two electrons will spend time around the nucleus of both hydrogens. They'll both feel like they have the noble gas electron configuration of helium. Because if I put another electron here, let's say they're both sharing this pair, they feel like they got their 1s orbital complete, like helium does, and they're more stable that way. And the way that you would write this is just H-H or H2. It all means the same thing. It's just two hydrogen atoms covalently bonded together. Okay? Let's look at oxygen. Now, oxygen has a valence of 6. So there's 1, 2, 3, 4, 5, 6. Electrons, valent electrons, because it's in group 6. It has 8 total. So if I fill my shells like we've been doing, there's 2, 4, 5, 6, 7, 8 total, which gives me 6, a valence of 6, because remember, valence is how many electrons are in your partially filled outermost energy level. So I have to look at the 2s and the 2p, and I count. I've got 1, 2, 3, 4, 5, 6. So that's a valence of 6. I can also tell that quickly without filling the electron configuration, because oxygen is in group 6. And remember, the elements are grouped in columns according to their valence. Okay, so everything in group 6 has a valence of 6. So oxygen gets 6 electrons around it. If I bring two oxygens together, okay, in order for it to feel like that it has the same noble gas electron configuration as neon, each one needs 2 more electrons, okay, to complete this 2p orbital. So if I give oxygen 2 more electrons, it will have the same electron configuration as neon. It will be more stable that way. Well, the way that it achieves this, and at least in the air, the atmosphere in this room, is 2 oxygens will come together and they'll share 2 electrons. And that forms a double bond, okay, a double covalent bond. So each oxygen is pulling on that extra set of electrons, and they're spending time around both nuclei. And so this would be a double covalent bond between diatomic molecule O2. You could write it like this. You could write it like this. Okay, either way, but it all means the same thing. It's just O2. That's the air that we breathe. It gets picked up by our hemoglobin in our lungs, carried to all our tissues, dropped off. Okay, that's O2. All right, now, that's the diatomic molecules. What about non-gases bonding to other non-gases? In other words, what if hydrogen bonds to oxygen? Okay, well, let's look at that. Let's put oxygen back up here. And this time I'm going to write its 6 valent electrons a little differently to illustrate a point. Okay, there's 2 of them. And then the other 2 I'm going to put down here. And I'm going to attach a hydrogen to each one. So when oxygen bonds to hydrogen, it typically bonds to 2 hydrogens, and that's what a water molecule is. Okay, it's going to form a covalent bond here, and it's going to form a covalent bond here to those 2 hydrogens. Now, oxygen feels like it has 8, 2, 4, 6, 8, because each dash is a pair of electrons. Hydrogen feels like it has 2, so it's like helium, and oxygen then would be like neon. So everybody's electrically stable. Their electron configuration is like a noble gas. It feels like the outer shells are full. That makes the atom more stable. If 2 hydrogens bond to 1 oxygen and they share all those valent electrons. Okay, so that's how it would look. It would look like a water molecule. I also made it in this triagonal bent structure because of the physical properties of oxygen being more electronegative. It pulls the electrons closer to it, and it takes that shape, that triangular shape. Water does. Let's try another one. Oh, let's say I do chlorine. This is another diatomic molecule. Chlorine to chlorine. Okay, well, I look on a periodic chart and I see chlorine is in group 7. It's got, chlorine has 17 electrons. So there's 2, 4, 6, 8, 10, 12, 13, 14, 15, 16, 17. So it just needs 1. It has a valence of 7, okay, because there's 7 in the outermost partially filled energy level. That third energy level has 7 electrons in it. I got to look at the 3s and the 3p. So I put 7 dots around it. Okay, and I put that single one on the inside on purpose so that I could bond those 2 chlorine atoms together. Because again, it's more stable that way. It will feel like argon. Its electron configuration will be like argon if it can have an extra electron orbiting its nucleus. Well, these 2 will bond together. Let me make a dash there to show you that. Now they're sharing that pair of electrons. That's what that dash means. Each chloride atom is sharing that pair of electrons so that it can achieve its noble gas configuration. So that pair of electrons is going to spend time around the nucleus of this chlorine, and it's going to spend time around the nucleus of this chlorine so that the whole molecule is more stable. All right? And you could write it like this, or you could write it like this. It means the same thing. It's just chlorine. Okay? It's a diatomic molecule, chlorine. What about hydrogen to chlorine? Well, first you draw the Lewis dot structure. There's chlorine. Here's the Lewis dot structure of hydrogen. Okay. They will share this pair of electrons right here because then hydrogen will feel like it has 2, and that will give it the noble gas electron configuration of helium. The chlorine will feel like it has 8, which will give it the noble gas configuration of argon. So they'll come together, and you can draw it like this. Or just like this. That's hydrochloric acid, by the way. Okay, but that would be the covalent bond between hydrogen and chlorine. All right. What about nitrogen bonding to hydrogen? Let's look at that one. Nitrogen has a valence of 5. And I can tell that quickly by looking at the periodic table. I've got a wall chart here, and I see that nitrogen is the first element in group 5A, and all the elements in group 5A have a valence of 5. Or I can just take the 7 electrons that nitrogen has. Its atomic number is 7, so that tells me it has 7 protons in the nucleus, 7 electrons orbiting it. The number of electrons and protons have to be the same because it's not charged. All the elements on the periodic table are represented in their neutral state, so they have equal protons and electrons. So there's 1, 2, 3, 4, 5, 6, 7. Okay? And notice I put 1 in each part of the 2p orbital, the x, y, and z, because I'm following these 3 rules right here. The off-ball principle, where I fill from the bottom up. Pauli exclusion principle, where each box only holds 2. And Hund's rule, which says that if they're at equal energy in the x, y, and z of the suborbitals of the 2p orbital are all equal energy, you have to put 1 electron in each before you start pairing them up. Because it takes more energy to pair them up. It's easier to spread them out. Okay, so that's how you would write the electron configuration for nitrogen. Well, that tells me its valence is 5, because the partially filled outer energy level is the second energy level and it has 5 electrons. So I put 5 dots around it. 1, 2, 3, 4, 5. Okay? And I'm going to bond it covalently with hydrogen. Well, each one of these single electrons is going to pair up with a hydrogen so that the whole molecule will be stable. Okay, so I'll put a hydrogen here, a hydrogen here, and a hydrogen here. Or I could draw it like this. Or I could just write it like this. It all means the same thing. It's just nitrogen covalently bonded to 3 hydrogens. One more I want to show you, and that is carbon. Carbon always makes 4 bonds. And the reason for that is because carbon is partially filled outer shell. Okay, it has, to start out, it has 6, 1 less than nitrogen. Okay, so it only needs 4. 1, 2, 3, 4. So that gives it a valence of 4. And again, it wants to have 8, so it can be like neon. So hydrogen or carbon will, if I'm bonding it to hydrogen, make 4 bonds. Okay? 1 to each hydrogen. So I could write it as this, CH4, that's methane. Alright, and that's carbon covalently bonded to 4 hydrogens. And covalent bonding in general. Okay, just to kind of summarize, covalent bonding is between nonmetals. Carbon is a nonmetal, it's a metalloid. Hydrogen is a gas, so they're both nonmetals. And it's not a transfer. The hydrogen doesn't transfer its electron to the carbon. Rather, it shares. Okay, so they share a pair. And they share a pair so that they both feel like they have a noble gas electron configuration. Hydrogen will feel like it has 2, so it can be like helium. Carbon here is going to feel like it's got 8, so it could be like neon, or have the same electron configuration of neon. And that's just kind of a little overview of covalent bonding.